let's take a look at this homework. 8.1 is page 587. 1 to 19, every other odd. I said 40, what did I say, 40 something to 43 to 55 every other odd. 43 to 55 every other odd. And then I said 61 to 73 odd. 61 to 73 odd. So which questions would you like me to go over? Were there any particular ones that people had a problem with? Or should I just pick a few and go over those? 1 to 19 every other odd. We also talked about the factorial simplifying, which is simplifying factorials over here. So going over this homework, anyone that people would like me to show them how to do? Should we do 11? 19? No particular ones? All right, well, I'm going to do number, let's see, 1, skip 3, go to 5, skip 7, go to 9, 13, I'll do 13 and 3, 5, and 17, 13 and 17. And then the next section, 43 to 55, those are very tricky. Those are patterns I want you to write equations for. So I'm going to do 43, and then I'm going to do a real tough one. Let's see. I'll do 45 and 47. 47. See if you can get those. And then 61 to 73 odd. Oh, right, we talked about recursive. I'll do 61. And then I'll do something like 65. And then I'll do 71. 65 and then 71. Okay, so I'm doing a lot of questions here. I don't know if there's time for all of these. But I want you to make sure you get, Benjamin, welcome. I want to make sure you understand how these work so you know how to input these problems and get your answers for these questions. So we'll go over these together on the homework. This is 8.1 homework. Hopefully we can get through all these. So let me quickly start with number 13 and show you how to do this kind of problem. So in 13, it tells you the equation, right? It tells you the equation, 1 minus 1 over 2 to the n. 1 over 2 to the n. And it wants you to have an equation. It wants the first 5 terms. Find the first 5 terms. Find the first 5 terms. So it gives you an equation, and it wants the first 5 pieces of it. So that just means you're going to plug in n for 1, 2, 3, 4, and 5. You're plugging in for n into this equation. This is 2 to the power of n, 1 minus 2 to the power of n. Plug in that equation, get the first 5 pieces. So a sub n, for each one, just plug in that n. n is 1, then n is 2, then n is 3, on and on and on. Again, if you're just joining us, Isaid, welcome. Jesus, welcome. Make sure you say hello in the chat. We're going over the homework from Friday about patterns, series, and sequences. Thank you. So the first one, if n is 1, this is going to be 1 minus 1 over 2 to the power of 1. Plug in the n, get your answer. So this is 1 minus a half. This is going to be 1/2. So the first piece, a sub 1, the first term in the list of patterns is 1/2. Next, n is 2. So I go 1 minus 1 over 2 to the power of 2. Right, which is 1 minus 1 over 4. 1 minus 1/4, that's 3 over 4. I should move this down a little bit. Let's move this down a little bit. Give myself some room here. Equals 1/2. This is 3 over 4. 1 minus 1 over 4, right? 1 over 4. 2 squared is 1 over 4. 1 minus 1 over 4 is 3 over 4. So this is my first term, second term. It's my third one with a 3. 1 minus 1 over 2 to the third power. You plug in the n, right? You just plug in the n. 2 cubed is 1 minus 1 over 8. Let's see, 1 minus 1 over 8, that's going to be 7 over 8. Because 1 is like saying 8 over 8, right? 8 over 8 minus 1 over 8, you have 7 over 8. Keep doing this pattern. 1 minus 1 over 2 to the fourth power. That's 1 minus 1 over 16. That's going to be 15 over 16. And last one, 1 minus 1 over 2 to the fifth power. That's 1 minus 1 over 32. That's going to be 31 over 32. See the pattern here? See the pattern here? Take 1 minus 1/2 is a half, 3/4 is 7/8, and this becomes our equation, and that's the pattern we have. So this is your answer. This list of numbers, this is the first 5 pieces of this pattern. From this equation, from that equation, you create this pattern here by just plugging in all the different n's. N is 2, 1, then 2, then 3, then 4, then 5. Plug them in, get your answers. Straightforward, right? And you can see kind of how some numbers maybe work out. You can see how some of this stuff can work out when you have 2 to the power of n. That's like all the exponents of 2, all the powers of 2. 2, 4, 8, 16, 32, right? All those exponents of 2. So there's certain groups, certain, I should say, equations that give you certain patterns. So 2 to the n is a certain pattern. Let's look at 17. This one, again, I want the first 5 terms. Find the first 5. I have my general formula, a sub n. My general equation of the pattern. It says -1 to the n over n squared. So there's my pattern. So again, my n, I'm going to plug in my first 5. 1, 2, 3, 4, and 5. And I'm going to get my answers. So if I plug in a 1, this is -1 to the first power over 1 squared. -1 to the first power is -1. 1 squared is 1. So -1 over 1 is going to be just, it's just going to be just -1. So the first number in my list is -1. Remember, we're creating lists of numbers. A sequence is just a list of pattern of numbers. Creating these patterns. For 2, I've got -1 squared over 2 squared. -1 squared, well, -1 times -1 is +1. 2 squared is 4, so this is 1 over 4. Next number, -1 to the third power over 3 squared. Let's see, -1 cubed. Well, with -1, if I do exponents, you know that just kind of tick-tocks back and forth. -1, +1. -1, +1. First power, second power. Third power, fourth power. Right? All the odd exponents get negative. Odd exponents stay negative. Odd exponents, right? Even exponents become +1. And so this is going to tick-tock back and forth. Not like the... I think that was a mistake, Roberto. I don't want to go to IKEA, thank you. Anyway, this is going to tick-tock back and forth with negative and positive, right? So negative 1 cubed is negative 1. 3 cubed, the 3 squared, I should say, is 9. So this is going to be negative 1 over 9. And so you see we have this like positive, negative, positive, negative. This is going to be a positive. This is going to be a negative. And you know you have that kind of pattern with this negative 1 to the n. So what's next? Negative 1 to the 4th power over 4 squared is going to be positive 1, right? 4th power, positive 1. 4 squared is 16, so it's 1 over 16. And then negative 1 over 25. And so you can see this becomes our pattern here. All the squared numbers, 1, 4, 9, 16, 25 on the bottom, all the squared numbers on the bottom. And it changes. Negative, positive, negative, positive, negative. And if we kept going, that pattern would repeat. So this little doodad here switches from positive to, or I should say negative to positive. From negative to positive. So this little kind of piece of like pattern here, this piece of a pattern is if you want your pattern to switch from negative to positive to negative to positive. That's the little thing you can use. A little like a little trick. And this squared here, this is all the square numbers. So we have all the square numbers on the bottom, 2, 4, 1, 4, 9, 16, 25, and switching from positive to negative. So little patterns you see in these equations. All right. So that was 13, 17. What else did I say? 43, 45, and 47. Let's see if I can do 43, 45, 47. So now that we have an equation and we get a pattern, oopsies. The next thing we're doing here, and this is probably the hardest part of this process, is if I give you a pattern, I want you to find the equation. Find what we call the general term, the general term, a sub n of the pattern, And so I'm going to give you a pattern here. We did this a little bit. 1, 4, 7, 10, 13. So we want to find the general term, this a sub n, of this pattern. So, first of all, what's the pattern? What is the kind of process here? What's the kind of, what do you notice about this? What are we doing each time? Are we doing something consistent each time? What's the kind of like pattern for this one? Thank you, Ricardo. Yes, plus 3. Looks like we're adding 3 every time. Plus 3, that's great. So we can come up with a general pattern, right? And we can do this either with an explicit formula, or we can do a recursive formula. I would accept either one, recursive or explicit. The recursive uses a n minus 1, right, previous term. And explicit only uses n. So what can we write for a formula that's explicit or that's recursive? We know we add 3 every time. So start with a 1. Add 3. So I know I'm adding 3. What might be an explicit formula for this equation? N plus 3? N plus 3? Well, not really, because if I do 1, that's going to be the first one before. 2 would be 5, then 6, then 7. That's not really what we need here. We're adding 3 each time. Maybe we could do a(n minus 1 plus 3. That would be the recursive formula, where a sub 1 is 1, where we start with our initial value. So that's a recursive formula. This just says take the previous number and add 3. Take the previous number, add 3. But if I wanted to use the explicit formula, I need a little bit more precision here. N times 3, yeah, right? N times 3. Well, not exactly n times 3, because if I plug a 1 in here, the first one times 3 would be 3. So that's too big. 2 times 3, that would be 6. That's too big, right? I want it to be 1, then 4. 3 times 3, that's 9. That's too big. But I can do something. I see all of these are off by a certain amount. 3, I want to go to 1. 6, I want to go to 4. 9, I want to go to 7. So it's not just n times 3. N times 3, and then I want to minus 2. Yes, exactly. Minus 2 gets me back to where I need to be. Minus 2. Minus 2, that gets me to 1. Minus 2, that gets me to 4. 9 minus 2, that gets me to 7. So I have my answers now that check out, and this becomes my explicit equation. That's how you got to figure out this situation, right? Find an n times 3, or figure out what you're doing, figure out the pattern. How many 3's do you do? And then what do you need to maybe add or subtract to get back to the original numbers? Very interesting, very interesting. And that's an easy pattern, everybody. Let's look at a more challenging one. 45. Or wait, 40. I said every other odd here, right? What did I say? 47? Oh, yeah, let's skip 45. I don't need to do 45. Let's look at 47. Hmm. 45 is very interesting, but let's look at 47. So again, find a sub n. Pattern is 2/3, and then 3 over 4, and then 4 over 5, 5 over 6, 6 over 7, dot, 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 dot. So what's the pattern? What can I write for my pattern here? 2 over 3, 3 over 4, 4 over 5, 5 over 6, 6 over 7. We see it's growing, right? Top and bottom are growing by 1 each time. That's interesting. If I add 1 to the top, add 1 to the bottom. But I can't really do that to fractions, right? I can't just say, take a fraction and add 1, right? It doesn't really work that way with patterns. I don't know. I can't just add a 1, right? But I do want to have a fraction here. And I want to involve n. So let's take a look at the n's. N is 1 here, then 2 here, 3 here, 4 here, and 5 here. So how can I look at this value, this n number, and the question is, how can I create this fraction using this n? Is a similar pattern everywhere along the whole group, right? How do I use this 1 to create this fraction? How do I use this 2 to create this fraction here, etc., etc.? Any ideas? Anybody notice how these numbers relate to the 1 and how these relate to the 2? Am I multiplying each time? No, not a multiply. What can I write? Again, tricky situation. It's going up by 1 each time, yes, but so are the n numbers going up by 1 each time. That's just the nature of the pattern, right? So I want it so that when I plug in a 1, I get 2 over 3. And then when I plug in a 2, I get 3 over 4. Right, so I want some equation where I plug in a 1 and I get 2 over 3. And I go up by 1, I get a 3 over 4. When you see it, it's going to be like, oh, of course that's the pattern, duh. But trying to figure it out, that's the hard part. Again, we want to use this 1 and make a 2 or 3. Here, I'll give you a hint. Both of these start with n on the top and bottom. I'm using the 1. I'm using the 1 on the top and the bottom. And then I'm doing something to it to get a 2 over 3. What am I doing to the n? N and an n. Use the n, use the 1, use the number. And then what am I doing to it? They're each going up by 1 only, so that's... I only need to multiply by 1, but I'm off, right? If this is a 1, I don't want it to be a 1 on the top. I want it to be... Noemi, tell everybody. Yes, that's exactly right, Noemi. There we go. N plus 1 on the top and n plus 2 on the bottom. Oh, of course. Look, it's 2 high. The top is 1 higher than the starting number, and the bottom is 2 higher. And every time we go up, it stays the same, kind of like the same, relatively the same. The bottom is always 2 times, 2 higher than the number, and the top is always 1 higher. Tricky, tricky. Right? Just look at them independently. If you think of the top pattern all on its own, all these numbers are just whatever the n is plus 1. And the bottom numbers are all the n's plus 2. And so we just put that as a fraction. Very, very interesting. Very interesting. So try that again for 51 and 55. 55 is very tricky. All right. So that is those. Let me do 61 and then 67. 61. So that's right. Finding this is probably the hardest. This part, probably the hardest thing. Finding a pattern from an equation. Finding an equation from a pattern. Probably the hardest thing. Everything else is just basically plugging in. So let me show you 61. This is a recursive formula. Recursive formula. We didn't really go over these too much, but let me show you how this works. So in a recursive formula, I give you a starting value. This is called your initial value. Your starting number, right? And then I give you the pattern. A of n plus 1 is equal to take the current number and or they use k. Well, whatever. Fine. K. Use k. That's fine. We'll use k. K plus 1 is take the current number. Take the current number, and it says to add to. Okay? And it wants the first 5 terms. So it wants it wants A1, it wants A2, A3, A4, and A5. It wants the first 5 terms. So A1, we know that is 6. It tells us right here. So A1 is just 6. There's nothing, no calculation to do. A1 is just our starting number. We got to start somewhere. With recursive formula, you have to start somewhere. A sub 2, well, if I use this formula here, A sub 2 is equal to A sub 1 plus 2. That's what this equation says. It says if I want the next number, if I want A sub 2, I got to use the previous number. Well, this is, A sub 1 plus 1 is A sub 2, is A sub 1 plus 2 more. So A sub 2 is A sub 1 plus 2 more. A sub 1 is 6, right? So A sub 2 is 6 plus 2. And that becomes 8. So 6, then 8. A sub 3. A sub 3 says, okay, if I want A sub 3, I need to use A sub 2 and add 2, right? Again, our pattern is take the next number to get the next one, use the last one, the previous number, and do something to it. Take the previous number, do something to it. So A sub 3 is A sub 2 plus 2. A sub 2 is right here, right? So you feed the last number into our next number. 8 plus 2, that's going to be 10. Same thing here. A4 is A3 plus 2. Take the last number, feed it into the next number. That's going to be 10 plus 2 is 12. And then clearly this is going to be 14. So 6, 8, 10, 12, 14. That is the first 5 numbers of this recursive formula. So that's how recursive formulas work. You take the previous number, right, this 6, you plug it into the next equation. Use it to get the next number. You build on itself. Different than the explicit equations, right? Explicit equations, like what we did here, right? Or here, we just plugged in directly. I didn't use the 1/2, right? There was nowhere, I didn't use this 1/2 to calculate anything else. I didn't use this, I didn't use the -1 here, or the 1/4. I didn't use the 1/4 anywhere in the new equation. I just had to use the n numbers. So for explicit equations, you just use n. Right? For explicit equations, you just use n. For recursive equations, you use the previous number n minus 1. N minus 1. And so that's what happened here, right? I took the previous number, used it in the equation. The previous number, used it in the equation. Okay? Let's try 67. Let's do 67. 67. So with 67, we introduce our next, our new kind of mathematical operator that we talked about on Friday. I want the first 5 terms. First 5 terms. Again, this is not recursive, but it is using our new tool called n. Right, everybody? N. No, it's not a loud n. It's n factorial. This is n factorial. Remember what the factorial did? Is factorial. Exclamation point means factorial. And it means if I had, for example, 5 factorial, that means multiply 5 times 4 times 3 times 2 times 1. You're multiplying all the numbers from the value you have down to 1. Factorial meant you multiply down to 1. It's not allowed n. It's not allowed n. It's a multiplication of values. So I want the first 5 terms with n factorial divided by 2n minus 1. So we have an explicit formula. We're going to use our n's. 1, 2, 3, 4, 5. Plug them in and find our first 5 terms using this factorial tool. Okay? Uh-oh. How much time we got left? 5 minutes. All right. Speeding through. N is 1. So this is 1 factorial over 2 times 1 minus 1. 1 factorial is just 1. 2 times 1 is 2. 2 minus 1 is 1. So that's 1 over 1, first term. 2 factorial over 2 times 2 minus 1. 2 factorial is 2 times 1. 2 times 1 is just 2. 2 times 2 is 4 minus 1 is 3. 3 factorial over 2 times 3 minus 1. 3 factorial is 3 times 2 times 1. All right, you just got to calculate all these numbers. That's going to be 6 over 6 minus 1 is 5. 4 factorial over 2 times 4 times 1, minus 1. 4 is, let's see, 4 times 3 times 2 times 1. 12 times 2 is 24 over 7. 5 factorial over 2, 5 minus 1, that's going to be 9, and that's going to be 120. So there you go, everybody. First 5 terms using this factorial. 5 times 4 times 3 times 2 times 1. So factorial just means multiply all the way down to 1. And that's the same thing we do in numbers 71 and 73. Simplify those factorials. Right? We know we can cancel out a whole bunch of things. Let me quickly do 71, just so you have it all. 2 factorial over 4 factorial. Just remember, this means 2 times 1 over 4 times 3 times 2 times 1. And we want to cancel out pieces. Cancel out chunks. So this is going to be 1 over 4 times 3, which is just 1 over 12. So with factorial math, right, we can just do these cancelings. Really simple. And just made it under the nick of time. Whew. Thank goodness. Questions, anybody? Issues, concerns with this homework? It's complicated. Do your best. Turn in what you have. It's due today. Get this done to me. Get this into me. Again, grades are due next week, so we are turning in our assignments this week. Make sure you have everything into me. We will start our next notes on the next topic on Wednesday. But that's it for us today, everyone. I hope this was helpful. Say goodbye in the chat. Once you say goodbye, you are free to go. I will see you later. Do that homework. Get that into me today. Thank you very much. See you all later.